Now we begin a new topic of actually trying to construct real numbers. But before we get into the technical details, we're just going to look at how do we represent numbers in new number systems, and in particular, how are we going to apply that to real numbers. So we're going to look at some examples of using existing mathematical structures and number systems to construct new number systems. We're going to see how we choose our representations from what we want out of our new number system. In particular, we're going to look at things that we couldn't get from the old number system that we want in the new system. We'll use that to identify at least two ways of representing real numbers. And then we'll choose one of them that will come out of Cauchy sequences, which we've been studying for a while now. So let's talk about making new number systems. Again, we want to use existing mathematical constructions. We want to be led by what we want out of the new number system that we couldn't get out of the older systems. And oftentimes we're going to have to use constructions that allow us to use more than one existing number to construct one new number. So one new number consists of maybe more than one number to help us pick that out. So an example from at least from two of the systems we're going to look at are ordered pairs. For real numbers, it's going to be a little bit different. So let's apply these principles to our favorite number systems. So in the beginning, right, all we have is sets. And so when we make the natural numbers, all we have is sets to make them. So remember, the way natural numbers work is you have a start to the natural numbers. For us, the start is 1, and then you have to tell how to get from your whatever natural number that you're at to the successor to the next natural number. And so we do that by saying, well, we do that recursively. We say 1 is represented by the empty set. It's a set. That's all we have. We got to represent it with something. And then every time we have a number n, we make the next number n plus 1 by taking our old number, which by the way is a set, and we union it with the set that contains n, which itself, remember, is a set. Okay, so we have all these weird increasing sets of things going on where we keep unioning. So that's how we make natural numbers out of sets. Now that we have natural numbers, we want to make those into integers. And let's actually take a step back on why we want integers at all. Well, one of the things that might have been frustrating to us when we had natural numbers is whenever we had to subtract, we had to be super careful that the first number in our subtraction was bigger than the second number. What we'd like is to have a number system where we can subtract any two natural numbers, no matter which one is the bigger one. So what we do in order to facilitate that is represent the integers with ordered pairs. And if this sounds familiar, it's exactly what we did in the first video. So don't feel like we're doing anything new. Well, new that you haven't seen before, I should say. So a and b are natural numbers, and a and b could be any natural numbers. It doesn't matter which one. A could be smaller, b could be smaller. They could be the same. And in our minds, conceptually, that ordered pair AB represents the number A minus B, right? So that, in some sense, allows us to subtract every possible number that we have. Now, we have to build some technical details on top of that to make sure that works, even when we have numbers that aren't natural numbers, but you get the idea, right? So once we have integers, we want to make rational numbers. And again, we identify something in integers that we're a little frustrated with. One thing that we have to be careful of when we have integers is division, right? We're only able to divide certain numbers. I can divide 9 divided by 3, but I can't divide 8 by 5, right? Because 8 divided by 5 does not give me an integer. So I know I'm never going to be able to divide by 0. That's a lost dream. That's something I'll never be able to do. But I would love to be able to divide by any non-zero number. And the way I do it is represent rational numbers, again, with ordered pairs A and B. So where A and B? Well, they're both integers, obviously, because those are the numbers that we have. B is not equal to 0 because, again, I've given up my dream of dividing by 0. And so A over B represents the fraction A over B. And again, if we're thinking about the operation, A comma B represents A divided by B. So we're sort of forcing us to say, hey, we are going to divide even if the integers didn't allow us. So now we're in the position where we have rational numbers and we want to make real numbers. And before we figure out how we want to represent them, we should ask ourselves what we want from them. And there are actually two reasonable answers to that question, right? First of all, we want every bounded above set to have a supremum, right? The whole thing that motivated us to create these new numbers is we wanted the completeness axiom, right? And so if that is our motivating goal, then that's going to help determine what kind of constructions we're going to have for real numbers. But there's actually another one that we have too once we start looking at Cauchy sequences. We want to make sure that every Cauchy sequences will converge, right? It is possible for a Cauchy sequence of rational numbers to converge to an irrational number, and that's something that we're missing in the rational numbers, is that it doesn't converge in the rational numbers. So what we want to do is we want to chase one of those goals with our construction. Which one do we chase? Well, it turns out we can chase either one. It's not that one is morally superior or logically superior to the other. They're just different ways of achieving the same goal. So let's say we want to chase the desire for every bounded above set to have a supremum. Okay, that's fine. Well, then one way of doing that is to represent real numbers by sets of rational numbers that are bounded above. And so in this case, these bounded above sets, so again, our real numbers are literally sets of rational numbers. And the only thing we're demanding of those sets is they have an upper bound somewhere. So the bounded above set represents the real number that is its supremum, right? So again, we wanted a supremum, so what we do is saying, hey, the supremum of this bounded above set may or may not exist in the rational numbers, but I'm going to say the supremum is the number that is literally the set. So the set is literally the number that is its supremum. And if you want to chase this particular construction, these are called Dedekind cuts. And so if you feel really motivated either during the class or maybe after the class, I can maybe find you a book where you can learn about Dedekind cuts. Dedekind cuts are really cool. They're really cool. But that's not what we're doing in here. No offense. We are going to look at Cauchy sequences. And so our motivating desire will be, I want every Cauchy sequence to converge. Okay, fine. So that means then we're going to represent real numbers with Cauchy sequences of rational numbers. And in that case, the Cauchy sequence of rational numbers represents the real number it converges to. Again, if I have a rational number that converges to an irrational number, if I'm thinking of it as a real number, then in the world of rational numbers, that basically does not converge because it's going towards a number that doesn't exist in the rational numbers. So literally, whatever the Cauchy sequence converges to, that is the number that we're representing by the Cauchy sequence. So that's what we get. So again, we are going to represent real numbers with Cauchy sequences of rational numbers, not because it's better. We're just choosing one. Whoops, sorry about that, pal. All right, so in our course, every rational number can be, so I want to first note that every rational number can be represented by a Cauchy sequence of rational numbers. So if Q is a rational number, here's a sequence that Q is represented by. It's pretty boring. I mean, Q itself is a rational number, so it can be a term in the sequence if it wants to. It could be, I guess it could be all the terms in the sequence. And that converges to Q, so it represents Q as a Cauchy sequence. If you want to get fancy, you could say Q plus 1 over n. That also converges to Q, so that represents the number Q. Q minus 1 over n, Q plus 1 over n squared. You can see that there are tons of Cauchy sequences that can represent the number Q. And that is just, I wasn't even being very creative. If you want to be more creative, you can find lots more. And what maybe you can see indicated here is that every real number can be represented by infinitely many Cauchy sequences of rational numbers, right? And if that kind of freaks you out, it's no different than what we've seen before, right? Just like fractions in the rational numbers, actually just like the ordered pairs in the integers. There's lots of different ways you can represent each integer. So the question is, how do we deal with multiple representations of real numbers? And I'm asking that like it's a question that we've never answered before. We've answered it before with integers. We've answered it before with rational numbers. And that is with, well, dealing with equivalent representations. And that is really talking about equivalence relations, right? So we're going to talk about equivalence relations, not in this video. I'm running out of time, but it will be in the next video. For now, there are some activities for helping you understand how to represent some real numbers. Just go ahead and click on the link below this video.